that you guys have come. I feel like this session might not be as useful if you haven't gone back and looked back at the material, because I won't have time to stop and explain everything step by step. I will be glad to entertain any questions along the way, but there's a lot of stuff that we're going to be talking about. Okay, and in addition to my PowerPoint, which contains a few memes, Molly's going to be entertaining you guys with some wonderful NMR memes as well. And if she can't find any, then she'll make some for you. All right, cool. So speaking of NMR, instead of usually going in the order that I go in, which is just based off of the order you guys learned this stuff in class, I am actually going to start with NMR. Well, sucks to hate NMR because you're gonna have to do it anyway. So learn to love it. Okay, so let's go and get started. So here is your first meme of today. So yeah, we're gonna be talking about all the different types of spectroscopy that you need to know for this exam, right? Here is a beautiful example of how a problem may look, but of course you're going to be looking at things like IR, mass spec, carbon NMR, proton NMR, and UV. Okay, so let's go ahead and get started. So for methods of structure determination, the whole point of spectroscopy is, if you're working in a lab and you run some sort of experiment, you want to find out if the experiment actually worked. So there are many different things that you can use. Some of them are going to be a little more advanced than others. But really the main thing that you can use to go and determine whether or not your reaction went to completion is spectroscopy, okay? So this is probably some of the most application-based stuff that you guys have been doing in this class, because without spectroscopy, research wouldn't be able to happen, and we wouldn't be able to synthesize some very essential organic compounds for use. This is in pharmacy and other applications. So the big things we're going to be looking at are IR, mass spec, UV, NMR, both proton and carbon. Okay, and as I said before, some of these methods are going to be a lot more useful than the others, and some of them are going to be a little more ambiguous, but ultimately everything serves a purpose, right? You're probably not going to use something like IR to fully determine a compound. If you happen to know how to solve a problem just using IR and mass spec, hit me up and I will gladly give you a thumbs up and maybe buy you a cookie or Venmo you to buy for a cookie or something, I don't know. Okay, but yeah, don't let the cookie motivate you too much. If that's gonna be too hard for you, obviously, we recommend sticking with NMR, okay? So I'm gonna be talking about IR first of all. So IR used to be very useful back in the day. I know Dr. Falzone loves to sometimes just solve a problem by only using IR, but for our purposes, it's pretty good for figuring out what kinds of functional groups are going to be in a molecule. So here is a rather complex or rather sophisticated IR, right? It's a lot more blown up than what you've seen before. Okay, you see that your x-axis is going to be wave numbers, so everything's going to be measured in wave numbers or centimeters to the -1. Okay, and then we see that we start off from 0 on the right and we go all the way to 4,000. Your transmittance is just going to be pretty much like where your peaks are going to be showing up. Okay, what intensity your peaks are going to be. So on the back of your exam, if you look at any back test, you're going to get a chart that looks a little like this. You have this chart of values that tell you specifically what kinds of things you're going to be seeing. So a CH bond that's bound to an alkane, an alkene, alkyne, aromatic, etc. And you're going to be seeing other things as well. So like what accounts for a carbon-carbon single bonds, carbon-carbon double bond, etc. And yeah, so you can use this to go in and figure out some pretty cool functional groups. I know for Orgo 2 over the summer, one of the exam questions actually involves something called an isocyanate, which is just nitrogen involved to double bond to a carbon, double bond to an oxygen. And that's something that you really can't determine by proton NMR or carbon NMR. That's where IR would be useful. Okay. For our purposes, for all the things that we're looking at, IR can tell you about a functional group, but other things like carbon NMR or your proton NMR can actually go and confirm those for you. Okay, so we're going to be looking at that. We're going to be working through a few examples, some easier, some harder, and we're going to see how we get there. And as you see, looking at this, everything is very ambiguous. You have a bunch of overlapping peaks all over the place. which is why I say it's good to narrow things down. Okay. Again, don't just rely on this alone, and don't feel too defeated if you're not too good at IR. Personally, I don't think I'm that good at interpreting IRs, or maybe I've gotten better recently, but yeah, IR is just not my thing, and I tend to maybe use that as a last resort unless something's very obvious for me. Okay, some rules of thumb for IR. So you're going to have a bunch of different regions in your IR spectrum, and we're going to be looking at those regions in that IR spectrum. Between 2,500 and 4,000, you're going to have bonds to hydrogen, right? So we're talking about CH, OH, NH, those types of things, right? Between 2,000 and 2,500, we're going to have triple bonds, 1,500 to 2,000 double bonds, and 1,000 to 1,500 single bonds. Past 1,000, there's actually something called a fingerprint region. Please completely ignore that, okay? Fingerprint region is really, really hard to interpret. We don't really use it in research in order to interpret our spectra, okay? So we just want to kind of like use the other ones, the ones that we can actually interpret better, to go and see exactly what groups we're going to have in our structure. Okay, a medium intensity spike indicates the presence of a double bond between two carbons. Oh no, it's actually indicative of a triple bond between two carbons. Whoa. Okay, hopefully the talking dog doesn't make you make that same mistake on an exam. Okay, so going back to this IR that I showed you earlier. So you see that this IR is actually representative of the compound that I've shown here. And labeling the regions that I've showed you guys earlier, remember that we said that this region in red, that's your fingerprint region, ignore that. Bonds, single bonds, double bonds, triple bonds, and then bonds to hydrogen, okay? So you see that there are some things that are rather identifiable. I've gone ahead and I've just denoted a few of these, okay? Not all of them. But looking from right to left, so starting with that little peak in your single bond region, i.e. the region in orange, you see that, sorry, your double bond region, my bad. You see that that's going to go and then correspond to an alkene, right? That's based on the that little chart that you're given on the back of your exam. This shows up between 1680 and 1600, so good for us. You see that region in purple over there. I've gone ahead and denoted two different peaks over here. So first you see that little peak between, I'd say, 2850 and 3000. If you actually go and then look, you're going to see that that is going to be indicative of a CH, particularly an sp3 hybridized carbon bound to hydrogen, right? Because we do have an sp2 carbon hydrogen, we also see that here as well. Most likely it's going to be that tiny little peak over there that you see right at around 2710, 2720-ish, but it's not labeled. Okay, and then lastly, you're going to see this big fat thumb over here. Okay, that thumb shows up somewhere between 32 and 3400, and this is actually one of your more characteristic ones, and that's going to represent alcohols. When we're looking at alcohols, we're looking at the ones that are going to be bound to hydrogens, right? So you see that your H-bounded alcohols on the bottom, that's going to be somewhere between 3200 and 3400. So that would likely represent your OH. Other particular peaks that might be of use to us will be maybe right here in our blue region. So we have some carbon-carbon single bond peaks, not interpretively useful because of course organic compounds are bound to have many, usually different carbon-carbon single bonds. But you see that some peaks over here at around 1300 to 1400-ish, those will typically represent carbon-oxygen bonds, which are going to be useful, but I do have a better way of finding carbon-oxygen bonds better by using your proton NMR. So that's what an IR looks like. Don't get too hung up on it if you're not understanding it or this kind of frightens you, because it's not going to be the most important thing for you. All right, Mr. Stark, I don't feel so good. Mind you, I made this PowerPoint in like 2018, so yeah, there's still lots going on here, or there's still lots of like 2018 type games going on there. Okay, so yeah, next thing we're going to be talking about is going to be mass spec. So mass spec, actually very useful because this is how we are able to actually go in and get our molecular formula from what we're given. This is going to give us an idea of how our molecule looks through fragmentation of important groups. So there's, I say, some important fragments to remember, but really there is not much remembering to know here because these fragments are entirely based off of molecular formula, right? So a methyl, which is going to be CH3, which would have a mass spec peak at 15. How do we know it's 15? Well, CH3 is composed of carbon and 2 and 3 hydrogens. Carbon has a molecular weight of 12, hydrogen of 1. So 12 plus 1 plus 1 plus 1 is 15. That's going to give you a methyl group. Add a CH2 to that to get an ethyl group, you get 29. Propyl, 43, etc., etc., etc. Okay. Some really useful ones might be phenyl and carbonyl showing up at 105, and then phenyl and ethyl showing up at 105 as well. Okay. If you have, you'd be able to go in and determine this further by going in and looking at carbon and proton NMR, but I wouldn't recommend using mass spec just for that, unless you're crazy skilled. Okay. Again, it's indicating the molecular weight of our important fragments, and the highest peak gives the molecular weight of the overall compound. Okay. Another big thing is that bromine and chlorine will exist in 2 different isotopes and then will cause 2 major peaks, one for each isotope. Now, bromine, has a molecular weight of 79, but sometimes you might see that it shows up at 81 as well. So 79 and 81, you're kind of going to have those 2 peaks showing up there. Same with chlorine, 35 and 37. So if you see kind of like 2 molecular weights for your mass spec, those just represents the 2 different molecular weights of or the 2 different isotopes of bromine and chlorine. Not too terribly useful because you have a molecular formula anyway. So here's how a mass spec looks like, and I'll show you guys some of the things that you can get from this mass spec. So particularly we have these peaks over here, right? So this peak at 77, so 77 is one that you should be aware of because it actually represents a phenyl group or a monosubstituted benzene ring, right? So that's C6H5. If you go and find the molecular weight of each carbon and each hydrogen, in total, that should give you 77. At 105, so again, you have possibilities between phenyl and ethyl or phenyl and carbonyl. You do have this oxygen here, so we can maybe potentially say that it's going to be the carbonyl that's next to the phenyl, right? Then you have a peak at 120, right? The difference between 105 and 120 is actually 15, which represents a methyl group. And then between 120 and 148, that would likely represent CH2s, okay? And again, because there's a difference of 28 and each CH2 is 14. So because of that, that would likely give you 2 CH2s, not necessarily next to each other, but somewhere plopped around within the molecule. Okay, so that's a little primer on how you should read a mass spec. Next up, I'm going to be talking about UV spectroscopy. This is going to be very quick because it only really tells you one big thing. And that's saying UV spectroscopy. It pretty much tells you if there's conjugation within your molecule, with some exceptions that are more complicated and not really in the scope of this class. But a conjugated molecule will typically exhibit a wavelength above 200, okay? Rare cases, you'll see it above 500, but typically 200 and 500 is your sweet spot. Your highly reactive systems are higher energy, and remember, higher energy has a lower wavelength, so those will be below 200 nanometers. So we're talking about systems that are not conjugated, right? We know that conjugation tends to stabilize compounds, so that will make that compound overall a lower energy. Likewise, greater wavelength, and hence a lower energy because of the fact that it is more stable, okay? Another big thing to get out of this is the fact that your lowest energy or highest wavelength UV transition will go from your highest occupied molecular orbital to your lowest unoccupied molecular orbital, okay? This is a type of problem that tends to get overlooked, but it was a quiz question last year that no one really understood how to get, so this is why I'm here to prevent that. Okay, so talked about this a little bit in Learning Then. Sorry, Sam, I almost just connected to your Apple TV. So we see here that we have, let's say, a compound like formaldehyde, right? We know that formaldehyde, the HOMO is going to be your non-bonding orbital on oxygen, right? So non-bonding on oxygen, and then your LUMO is going to be your pi star. So if you were to be asked what your lowest energy transition is, your answer would just be non-bonding to pi star. Okay, another example, let's say we had a compound that looks like this. Okay, again, your HOMO here you see is going to be your pi bond. And then your LUMO is going to be pi star. So your lowest energy UV transition, in this case, because your HOMO is pi, your LUMO is pi star, is going to be pi to pi star. Cool, not much, the most complicated thing about knowing this is remembering what the HOMO and LUMO is gonna be. Remember, as I always say, exam 1 and exam 2 stuff never goes away, or any other exam in Orgo, but just remember you guys are on top of that because those are going to be very well applied into problems like this, what you see here. Okay, so that would kind of be just like a one-off question. You might not necessarily be asked to find the lowest energy UV transition for like a spec problem, might be its own separate problem, but good to know this stuff nonetheless. Right, back to the PowerPoint. And yeah, that's pretty much it for UV spectroscopy. UV spectroscopy on its own is almost useless. But if you're ever concerned about whether or not a molecule is complicated, this is, not complicated, conjugated, then this is a pretty great way to go and check that out. Okay, and back in 2018, this review session was a lot closer to Halloween, but since Halloween just happened like last week, woo, okay, cool. So yeah, if anyone actually went and like carved a pumpkin that was a proton NMR, then good for you. Seems like you're really liking the class then. Okay, but yeah, NMR is the big boss for us. So we want to go and then tread pretty carefully with this. So our big focus is going to be proton NMR and carbon NMR. So I'm going to start off by talking a little bit about carbon NMR. So your carbon environments in your molecule, right? And that's talking about different, completely magnetically different places that are going to be within your molecule, or different environments rather. So show an example of that. Yeah, sorry, I'll be switching back and forth between my laptop and my iPad for at least this first spec part. Okay, so let's say we have a compound that looks like this. Actually, let's just do this one, just to show a more simple example. Now, first you want to go and then try and find where your line of symmetry is going to be if you have one. Okay, symmetry will help you out, or understanding symmetry will help you out a lot. Okay, so we see that we have a plane of symmetry going right here down the middle. Okay, is that a well-drawn plane of symmetry? Here, let me make the molecule look a little nicer so it doesn't get confusing or anything. There we go, like this. And then using this, we actually want to go ahead and then find out where our, we're going to find out like which environments are going to be equivalent. Okay, so let's look at the methyl groups, for example. You see that this methyl group is going to be exactly the same as this methyl group over here, right? Because they're just the same group that's about that plane of symmetry. Cool, so that's going to be one of your environments. Another one is going to be this carbon over here with no hydrogens, also bound to this carbon. Or not bound to, but those two are going to be the same. Here's this one and here's this one. There's another one. And then you have another environment over here that's kind of its own thing, not on the plane of symmetry or in the plane of symmetry. And then you have another one right over here. So we're talking about 5 different environments, okay? You know that this gray one and this blue one are not going to be the same because the gray one is much closer to the methyl groups than those blue ones are, and this blue one is. Okay, so since we have 5 different carbon environments, we would expect 5 peaks here. Cool, there we go. Let's go ahead and compare that to a molecule that's not symmetric. So let's say we have maybe something that looks like this. Okay, well, here there is no plane of symmetry, or no plane of symmetry for the compound with respect to the carbon environments. So because of that, that means that every single carbon is going to be a different environment. So we're saying this one's an environment, This one's an environment. This one's an environment. This one's an environment, and this one's an environment. Okay. You could. Oh, sorry, it's kind of lagging here. Yeah, but you could tell that these are going to be 5 different environments because of the fact that each of those carbon peaks is like progressively getting closer and closer to that bromine that you see there. Okay, so here we see that there's another 5 carbon-13 environments. Okay, so big moral of the story that separates this from proton NMR. Carbon environments count. Whether or not they contain protons. Okay, so that's pretty much telling you like why this red signal over here shows up as a peak, even though that there's no proton signal. Now, if we're looking at proton environments, then this over here would not be a proton environment because there are no protons there, but we'll talk about that in a little bit. Let's shift back over to PowerPoint. So chemically equivalent carbons will result, as I said, from symmetry. So you shouldn't loosely just use your carbon NMR to determine how many carbons are in your molecule. Again, you have molecular formula for a reason. So if you have, let's say, 8 carbons in your structure, but you only have 5 carbon peaks, and that means that there is bound to be some symmetry in there somewhere. So the advantage that it has over proton NMR is that it could tell us about carbons that do not contain protons on them, right? So if they don't contain any protons on them, then that'll help you go and then see things, which makes it really useful for finding out things like carbonyls and other things like that. Okay. And there are many different types of carbon NMRs that we're going to see. So this next part is going to be really important because different problems utilize different types of carbon NMRs. So the most simple one that we can see is something called our proton decoupled carbon NMR, right? Proton decoupled essentially means that we are not going to be using, we're going to be looking at any carbons that are not bound to, that are or are not bound to protons, meaning that whether or not it has a proton on it does not matter. Okay, so this is the simplest type you can get, but it also might be the hardest one because it gives you the most limited amount of information. So you see on the top right corner, you're going to be given a list of peaks, and they're all listed from downfield to upfield. If the number has no asterisk, like for example 166.1, then you're not going to have you're going to have an even number of hydrogens on that carbon. And by even, I mean, that technically also means 0. So 0 or 2 protons on that peak. If you have an asterisk, that means that you have an odd number. So either 1 or 3. And I want to turn your attention to this tiny little blip over here at around 78 parts per million. That's going to be your characteristic peak for deuterated chloroform. Okay. Deuterated chloroform is just a solvent that we need to take these NMRs. It's not actually going to be important for actually solving the problem. Okay. So if we look at all the peaks that we have here, so starting from downfield, you see that you have a peak, you have this first peak at 45.9, has an asterisk, so that means that it's going to have either 1 or 3 hydrogens. Moving right along to the next one at 57.2, because there is no asterisk, there will be 0 or 2 hydrogens bound to it. Then we have this peak at 63.4, which, because it has no asterisk, it's also 0 or 2 hydrogens. Moving right on to the next one at 128.7. This does have an asterisk in the list over here. So that means that you're going to have 1 or 3 hydrogens. Next one is going to be 136.4, 0 or 2 hydrogens. And lastly, this tiny little blip over here at 166.1, it'll be 0 or 2 hydrogens. Now, if you're given this list, it's actually going to be really quite useful for you, particularly because I don't know about you guys, but for me, sometimes I tend to miss the really, really small peaks. Like, honestly, I probably would have totally missed this peak at 166 if it weren't for this chart. So when you're counting your carbon environments, if you choose to do that, make sure make sure that you guys are going and double checking with your list. Okay. Again, this is the simplest type that you can get. Gives you probably the least amount of information, but the other two will be maybe a little more useful for you. This next one is called the depth. Okay, and this one only shows carbon. So the depth, which is the one up here, only shows carbon environments containing hydrogens, right? Um, the depth is most useful if you have your proton decoupled along with it, which is why in any spectra that you see a depth, you'll have the proton decoupled given along with it as well. The thing with the depth is that it won't give you every single environment if you have carbons that don't contain any hydrogens on them. Okay, so you see that here you only have 3 peaks, but down here you look and you have a total of 6 different peaks. This actually, there's a reason for that. Okay, so the idea is that the depth is based off of this legend over here, and you see that CH3 and CH both, they have an up arrow next to them. This means that if you have a peak that points up, like these two over here, that means that you're going to have either 1 or 3 hydrogens bound to that carbon. Not too terribly useful, but what does make things useful are the next 2 things, which are if you have a CH2, any carbon that has a CH2 will have a peak that points down. So you see this peak over here at around 41 points down in the depth. So because of that, you know that will have to be a CH2. And then you see these peaks over here, these 3 peaks, not including the solvent, of course, that do not show up in your depth. And if you have a peak that shows up in your proton decoupled, but not your depth, what that's basically saying is that you do not have any carbons bound to those peaks. Okay, again, because the depth only shows the carbons that contain protons. So let's go ahead and then analyze this once again. So you see that this peak up here, this one at around, let's say 28-ish, it's pointing up. So it means you're going to have either 1 or 3 hydrogens on that. Next one is going to be the peak that you have at 30. You see it's also pointing up, likely going to be 1 or 3 hydrogens. And then you get to this peak at around 41. You see that it's pointing up in your proton decoupled, but down in your depth. If it's down in your depth, you could safely assume that it's going to be a CH2 carbon environment, or a carbon that contains 2 hydrogens. Now, looking at these 3 over here, these 3 all do not show up in your depth. So because of that, you'll have 0, 0, and 0. Cool. Useful information for us, but again, proton NMR is more useful. But honestly, I would not ignore carbon NMRs for various reasons, and we'll see that when we get to our examples. Our third type, in my opinion, I haven't seen this one as much, but I certainly have seen it. This is going to be your off-resonance decoupled. And this one actually looks pretty similar to a proton NMR. It's actually based off of your N+1 rule. And that actually goes and then uses that to reflect how many protons are bound in each carbon environment. The reason why it's useful to include the proton decoupled here is because of the fact that sometimes you might look at these peaks and say, is this actually a quartet, or is it just 4 or like 2 or 4 different peaks or something like that? Well, you can actually go and then double check it. Okay, so you see that this one peak will split into this quartet. This one peak splits into this quartet. Solvent, ignore that. This one peak splits into this doublet, and this one peak just remains a singlet. Okay, so the rule is that if you have a quartet, for example, then you're going to have 3 protons bound to it. Triplet, 2 protons. Doublet, 1, and then singlet, 0. So you see, first up is your quartet. Because you have 4 peaks there as a quartet, that's going to be 3 hydrogens, so a CH3. Another CH3 right here because it's a quartet. Ignore your solvent. And then you see that you have this guy right here, which splits into 2. Because it splits into 2, that's only going to be 1 hydrogen. And because the last one is not split at all, you have 0 hydrogens on that carbon. Okay. So yeah, these are the 3 main different types of carbon NMRs you can see. Make sure that you guys are comfortable with analyzing all of them, because proton NMR, as useful as it is, sometimes does not work that well alone. So you got to make use of the other resources that you have available to you. Okay. Any questions about anything I've talked about so far before I move on to proton?
Yeah, so for these peaks, sorry, like just to clarify, so you said that there's like 4 peaks, but 3 hydrogens. Um, so does that like indicate the 3 hydrogens on the neighbors or on the actual carbon that we're referring to?
Great question. So for carbon NMR, we're talking about the carbon itself. The only time you're looking at your neighbors is for proton NMR.
Okay.
Mhm.
So this one would tell you that since it's 4 peaks, it's a CH3 that we're looking at.
Yep, that's right.
Okay. And sorry, why was it that had 4 peaks then?
Because it's just split by each of the protons that you have there, right? You can consider like the distance between each peak to be one of the protons. That
Oh,
makes
I
sense.
see. Okay, cool. Yes, thank you.
Mhm.
Juan,
Yeah,
does the height of the peak mean anything in carbon NMR?
not necessarily. Really, the best indication of like the best indication that an intensity can give you would be the integration from your proton NMR.
Okay, sounds good. Thank you.
Mhm. Okay, let's go ahead and move on to proton NMR. Very important discussion. So our proton NMR is going to help us gauge, of course, the proton environments that we have in our structure. Okay, so if we were to go back and look at the spectra that look at, like, for example, the examples of the molecules that I gave you earlier. So if we go and then look at this and I ask you to find how many proton environments there's going to be, you're going to have to go and then look at all the places where you have protons bound. So let me go and then erase all this little color coding so we can take a look. Okay, so we see that these two groups at the end, they are methyl groups. So they contain protons, so they're a proton environment. These groups right here, we look at them, they actually have a hydrogen that is directly bound to it. Because of that, that counts as another environment. Okay, you have another one that's over here on the bottom, and then you have another one over at the top, okay? Unlike previously, this peak that you see over here is not going to be a proton environment because there are no protons attached. Okay, so because of that, even though we had 5 carbon environments, we would only expect 4 proton environments here. And then for our other one, we actually have, we actually see that all of our carbon environments contain protons. So here we would say that we have a total of 5 proton environments as well. Again, you know that because you know that this guy's going to be a CH3, CH2, 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 CH2. All of those guys contain protons, so they're all viable for proton environments. Okay, there are some more examples of things that of other ones too, but you'll see that each peak not only is represented in your proton NMR, but also might appear, or you expect it to appear as different types of signals or different shapes based off of the number of protons that they have and also the neighboring groups. We'll see that in a little bit. The easiest way to do it, as you guys have maybe seen in my learning done, is to make a chart. I know that in lecture, Dr. Falzone doesn't usually make a chart. He kind of just goes and then directly connects peaks to where they'll be in the molecule. I don't know about you guys. I personally find that, especially when I'm learning, to be a little tricky, because after lots and lots of practice, you'll be able to go and then connect things as well as he can. But for starters, I think it's really important to go and then organize your work as best as you can, right? The thing I've told some people that the thing that I like about this compared to things like stereochem or constitutional isomers is that there's actually a pretty nice and systematic way to get things here, right? Of course, granted, you'll have some nuances sometimes, but it's not like stereochem where I can force you to look some way, where I technically have to force you to look some way, or constitutional isomers where I have to force you to think some way. Okay. But before we go and then look at that, it's important to go and then learn about what some of the terms mean, because we throw around lots of terms, and often you might feel like you're a little confused as to what they actually mean. Okay, so the first term that we have is going to be resonance. And you guys have seen the word resonance before, but in a totally different context. When we talk about resonance, previously we were talking about, you know, the delocalization of electrons, right? But here we're actually talking about the individual signals that you see on your NMR, right? So if I say I have a peak at 3.8, I could say, oh, I have this resonance at 3.8. Let me go and analyze it, right? So just, you know, whatever, like any like group of peaks that you see there is going to be a resonance. Chemical shift, that's actually the x-axis of your proton NMR, and that pretty much tells you, you know, where the peak shows up, but at the same time, it can also help you gauge things like, oh, like what groups is my proton environment going to be next to? If you're very downfield, or if you're very to the right, so to the left of the spectra, you're probably going to be next to some electron withdrawing group, right? But if you're very upfield or to the left, to the right of the spectrum, then you're probably going to be, you know, not really next to any electron withdrawing groups. Okay, again, we'll see many examples of that in the 3 examples that I have prepared for you guys. Multiplicity, or sometimes called splitting, that's going to be the name that you're going to be giving to your peak based off of the number of peaks it contains, right? So if I have a resonance that has 4 peaks, I'm going to call it a quartet. If I have 6 peaks, I'm going to call it a sextet, right? And this pretty much tells you how many adjacent proton environments you're going to have to the proton environment that you're analyzing, right? Typically, we mostly exhibit 3 bonds coupling, so that's why we have adjacent environments. And it's also going to be based off of the n+1 rule, right? So for example, if I have 4 adjacent protons, right, then that means that my peak is going to be split 4 times. And if I split it 4 times, I end up with a pentet. Okay, that's kind of where the n+1 rule comes into play. So if you have a pentet, you kind of have to go and work backwards to see that it's likely going to be next to 4 neighbors. Integration is going to correspond to the ratio of the number of hydrogens that you see present in your structure, okay? Integration, I mean, we typically see it as just like the number of hydrogens, but you might actually see it as a ratio. And this is where things might get a little tricky, because just write down a little example here. Let's say I have a compound with molecular formula C7H14, and my integrations are going to be 2, 2, 3, right? The big thing that you guys want to know about your integrations is that you want these to add up to your number of hydrogens in your molecular formula. Okay, so if you see them represented like this, 2, 2, 3, that adds up to 7. Right, and obviously, I hope you guys know from elementary math that 7 does not equal 14. Okay, maybe in the electoral college, just kidding. But you see that if you wanted to go and then get that to add up to 14, then you'd have to go and then multiply that by 2. Okay, so by that means that your integrations would actually be 4, 4, 6. Okay, and doing that will give you a total of 14, which is what you want for your molecular formula. Okay, another example, just to see that it doesn't necessarily have to be just by 2, but let's say I have a molecular formula of C7, or I don't know, 7, let's do C10H16, and my integrations are just 1 to 1. Okay, so if you see 1 and 1 there, then that does not mean that, I mean, you're going to see that those add up to 2. Okay, but of course 2 does not equal 16. So you want to go and multiply these, or so that they do end up adding to 16. Okay, so you know that 2 times 8 would give you 16. And then 1 to 1, so multiply these by 8, and then you end up getting that your integrations would actually be 8 to 8 instead. Okay, so I often get asked, so what if it's the case that, like, I don't know, it's a molecular formula of, I don't know, C10H16, and I see that my integrations add up to 13. Well, there's only one answer to that, and that there's a typo in the problem. So if that probably won't happen, but if it does happen, then notify your TA or Dr. Falzone and that will be fixed. Yes, it has happened before. Okay, so, okay. And then of course, degrees of unsaturation, you guys know that from way back when. Remember that that's going to account for the decrease in the number of hydrogens from that CnH2n+2 formula, or your saturated alkane formula, right? There's a little formula associated with it that you see down there. I personally am not a big fan of that formula. I've never really used it, but it's there for you in case you need to, in case you happen to forget how to find it. Okay, and it's bound to give you the right number of degrees of saturation, provided that you know what you're doing. Okay, so now that we have some basic definitions, what better to do than to look at more basic definitions? Well, first, before we go into more definitions, I'm going to be talking a little bit about hydrogen bonding. So I'm going to be talking specifically about broad singlets. Okay, so broad singlets are represented by BS. Hopefully, there won't be too much of that on your exam. But essentially, whenever you have a broad singlet, it indicates that you have hydrogen bonding going on. That is an OH or an NH within your compound. Okay, so really, all you have to know that it's just going to show up as a broad singlet. And sometimes you're going to see that it exchanges with solvent, right? It only really exchanges with solvent and protic solvent. So like, let's say you have a peak that is a broad singlet and it says exchanges with D2O, then that means that it's going to be an OH or an NH. How do you know? Well, you have other tools to figure things out. Little word to the wise, if your molecular formula does not have an oxygen and you put an alcohol, I don't know, it's probably wrong because alcohols have an oxygen in it. Okay, so like, yeah, let's say you have a nitrogen in there, an NH, or it would be based off of an NH, right? Sometimes the peak won't look very obviously broad. So because if it's not broad and it says exchanges with D2O, then it's still going to be a hydrogen bond. Okay, so yeah, so like if you either see broad singlet or you see either broad singlet or exchanges, then that's going to be one of those. And then just know that hydrogen bound protons are not split and will not split adjacent protons. What I mean by this is that when you go in and figure out your splitting, so let's say we have a compound that was probably consumed by many people this week. Okay, when you look at this, you're going to see that, this guy is going to, you have some adjacent protons here. So you see that this one actually only gets split by the CH3 that you see here. Okay, so that's why this guy would actually show up as a triplet, not as a quartet, because of the fact that this guy will not split that CH2 there. Okay, likewise, yes?
Wouldn't it be a quartet because it's the 3 plus 1?
Yeah, it is a quartet.
Sorry.
No, don't be sorry. Good catch. Yeah, so quartet because 3 plus 1. Apparently I can't count. Okay, and then over here, like you see, this of course is it's not going to be a triplet, it's just going to be a broad singlet. So BS. Screen is laggy once again. There you go, BS. Okay, so make sure that you don't try and like couple a CH to an OH or vice versa, or a CH to NH or vice versa. Okay, back to the PowerPoint. All right, and then let's talk about back to definitions as promised. So we have 3 different types of protons that we can see with our spectrum. One of them is going to be homotopic protons, which means that replacing a proton with another atom will result in 2 identical molecules. Okay, homotopic protons, these are surprisingly very, very common, and they are going to have identical chemical shifts. So here's an example of how that will look like. So let's say we're starting with this compound in the middle over here. If I go and then replace that red proton with deuterium, then I end up getting this compound. And if I end up replacing the blue proton with deuterium, I end up getting this compound, okay? Notice that here I'm not creating a new chiral center. If I were to be creating a new chiral center, then it would probably be homotopic or diastereotopic usually. But because I'm not initiating any stereochem of any sort here, this would be homotopic. I can certainly go and flip this molecule to get this, so they are identical. Enantiotopic, same idea, but instead of having identical molecules, you're going to be getting enantiomers, okay? Enantiomers, for you guys' purposes, are going to have identical chemical shifts, okay? That's all you need to know. If you're going to be working in research lab and you decide to take your NMR in a chiral solvent, it might be split and potentially make your NMR a little harder to interpret. Okay, so that's why you want to try and be careful with the solvent that you use to take an NMR. So that looks like this. Now you see that your molecule is not symmetric like the one that you see here. And if I were to, whether I was to go and then replace this, either of these hydrogens with a deuterium, as you see here, you end up seeing that they end up being enantiomers of each other. Meaning if I were to go in and find my absolute configuration, you would end up seeing that this compound on the right is going to be S, and then this compound on the right is going to be R. Cool. So R versus S, of course, they're not identical. You cannot rotate an R to get S, so they have to be enantiotopic. Oh, I have lost my mouse. There we go. And then diastereotopic, same thing, except now you get diastereomers. Diastereotopic protons are actually the ones that kind of go and then make your life a little more challenging because they actually show up at very, very, very distinct chemical, or not very, very slightly distinct chemical shifts. That's what I meant. Okay, so like let's say you might have diastereotopic protons that show up at 1.3 and 1.2. Okay, sometimes you might be a little overlapping. That's the case. Consider the fact that you might have some diastereotopic protons. That looks like this, what you see here. Okay, particularly what's driving this to be diastereotopic is that you're initiating stereochem, but you already have a little bit of stereochem in your compound. If you were to go and then find the absolute configuration of the alcohol that's already there, then you get that it's going to be S. Likewise, if you were to go and then find the absolute configuration of the other thing, of the other new chiral center that you formed, you end up getting that it's going to be, this is going to be S, and then this is going to be, oop, I put this one on the wrong one, R. Cool, so we have RS versus SS, those are going to be diastereomers, okay? And just remember that you can get diastereomers in a multitude of different ways, right? So if they, what's it called? If you see that you have different diastereomers being, you know, with that chiral center or maybe cis-trans possibilities, then know that they will be diastereotopic. And of course, I know you guys all have your model kit from exam 1. So if you guys feel like this is tricky, don't hesitate to go in and build your models and see how they might be one of these 3. Okay, let me, cannot find my mouse again. Well, so that's going to be an homotopic, enantiotopic, and diastereotopic. And then you see that you're going to have these shift tables at the end of your exam, right? You can always use these shift tables to go and then narrow down your options if you're given if you're given an IR, right? So again, you see that things are overlapping, but you're always going to have possibilities for things that might be, for things that might be easier, or the things that might be on your molecule. So quickly going to show you guys my annotated versions of these shift tables. All right, so here are going to be the 3 main shift tables for NMR that you're going to be getting. The top 2 that you see here, these 2 are going to correspond, these 2 are going to correspond to carbon NMR, and then this bottom one corresponds to proton NMR, okay? Feel free to take a screenshot of this, but you're going to be seeing some very, very, very common, some very common things in between, okay? So let me let me erase this because I got this from a learning done session. Yeah, but you see that in your carbon NMR, peaks that show up above 160 will represent carbonyls. This is more amplified up here. And you have things like aromatics and saturated alkanes to take care of. I personally think carbon NMR is very useful for carbonyls. Then over here, you have things like carboxylic acids or aldehydes, aromatic regions, just to go and then name a few, okay? A lot of the questions that you guys might have about why something is oriented a certain way will come from this shift table. So maybe before you decide to like ask, oh, why is this oriented this way and not another way? Think back to the shift table, and the shift table will most of the time give you the answer, okay? If not, then feel free to talk to one of your friends and like see how that works, okay? Because these shift tables, I'm telling you guys, they are very, very important. They tend to get overlooked, okay? So I've told my pilot kids that I will likely be quizzing them on some important shifts. So if you're not in my pilot, pretend that you're in my pilot and maybe think like you're gonna be quizzed on some of these shifts, okay? Cool, so yeah, let's go ahead and work on simple-ish practice problem. Okay, so you see what I've done here is that I have first gone and color-coded the spectrum. I know it's a little blurry, but I give you, or all the information is given for you up here. And I have gone and then created a table based off of the shifts, okay? So I'll tell you guys what's in this table. First, this is your chemical shift. Chemical shift honestly does not have to be exact, okay? If this is if I say this is 3.4, but you say it's 3.3, no big deal, does not matter. Okay, so I've gone ahead and I put my 4 shifts over here, roughly to where I think they're at. My number of hydrogens, or that hashtag H that you see there, is going to be your integrations. So 2, 2, 2, 3. So I went and I aligned that with those that you see there. And then your multiplicities are going to be your splitting pattern. You see that these are the 4 splittings that you're going to be seeing for these peaks, okay? In a problem like this, whenever you see that these integrations and these splittings are listed like this, they are listed from left to right. And I know a question that a lot of you are burning to ask or find out, am I going to be given this information on the exam? Yes, you will. Now, integration, for sure, you're going to be given, okay? Don't bust your butt going to Home Depot or Office Depot or something to go and then get a ruler, because that's really the only way that you would be able to find integration, okay? That'll be given to you. Splitting, the only reason the splitting will not explicitly be given to you is if the spectrum is really easy to read or if it's very clear. Now, obviously, this is not very clear, very blurry, but if it's given to you up here, then that'll be good for you. Okay, so now with that given, let's go and then find out what we can potentially have here. First thing I might want to do, and learning done people know that I'm very notorious for forgetting to do this sometimes, is to take your molecular formula and find your degrees of unsaturation. So how many degrees of unsaturation do you guys have here?
None.
Yep, 0 degrees of unsaturation. Excellent. So no rings, no double bonds, no triple bonds. Now we want to go and then kind of look at what we have here and see how we can go and solve this problem. Okay, so first, and I see what I have here is this integration of 3. Now, things that show up very upfield, like close to 1, like you see here, those are going to be, things that are like in the saturated alkane region. They're pretty far away from electron withdrawing groups. Okay, so if you see this peak that integrates to 3, that'll likely be a CH3. So I'm going to put that here in blue. And you see that I have a triplet. If I have a triplet, that means that I have 2 neighbors. Well, if I have a CH3, I mean, I can only have 1 extra thing bound. So the only way I can have 2 neighbors with that CH3 is if my next door neighbor is a CH2. Okay, so we good so far. Now, the next thing I want to go ahead and then find out is maybe, like see if there's any other things that like might ring a bell here. Personally, I think something that looks really attractive to me is the fact that I have this peak here at 3.4, right? Notice that everything here is relatively upfield, and then this guy's just downfield for some reason, okay? So you see that it's a peak that integrates to 2 and is going to be a triplet. So what I'm thinking is that if it integrates to 2, it'll most likely be a CH2. That's bound to another CH2. But I kind of want to sit here and question why that's appearing so far downfield, right? Remember, everything pretty much happens for a reason, unless, I mean, I guess unless it's spec, because sometimes you look at stuff and it's like, oh, this isn't for no reason, and it's usually some quantum mechanics stuff that you don't know, but I digress. So if you look at this, you see 3.4. If I go and then look back at my shift table, I see that alkyl halides usually show up somewhere between 2.1 and 3.5. So again, this is based off of knowing how to read my shift table. So I'll just leave that there for you guys. Alkyl halides 2.1 to 3.5. That likely means that this CH2 will be bound to another CH2 on one side, and on the other side, it'll be next to my bromide. All right, cool. So I have two of my CH2s. Or sorry, I have one of my CH2s, one of my CH3s, and then my bromine next to that CH2. Now I want to go and then see what I have, left. So if I look at this CH2 over here, it's next to the CH3. Because I know for a fact it's already next to that CH3, I know this has to be at least a quartet. Okay, because having 3 neighbors is already going to be splitting it by 3, hence making it a quartet. Okay, likewise, this guy right here, I know it has to be at least a triplet. So I want to go and then keep going and see if there's any possibilities that I can have with this. Well, if you see this peak, that's a sextet over here. So it'll be a CH2 that I know has 5 neighbors. Well, a really good way to have 5 neighbors would be to have a CH3 on one side and a CH2 on the other side. Okay, with a CH2, that's pretty much the only way you can get a sextet. Okay, those 5 neighbors that you see right there. And then for that last pentet that you see over here, you see that pentet would have 4 neighbors, pretty easily could be a CH2 that's smushed between 2 CH2s. Right as you see here. Cool. So now that we have all of our fragments ready, we can go ahead and actually piece everything together. So I see that I have this CH3 first. And very conveniently color-coded, I see that this CH3 would be next to the yellow CH2 that you see here. This yellow CH2 likely going to be next to the red CH2, right? And then I know that this CH2 has, that last green CH2 has to be at the end and next to your bromide. Okay. So that gives us this structure here as our final answer. Cool. So it's always good to be pretty systematic. Of course, I've done this problem multiple times, so I'm good at it. But you see that by taking things nice and slow and thinking about where things belong, you can, and of course being organized, you can pretty nicely go in and solve this problem. And you might have some sort of a, what's it called? You might be mistaken sometimes, but this kind of reduces the margin of error that you might have for this. All right, cool. I do have 2 more, but I'm not going to have time to go over them. So I will give you guys some extra practice, and I will, so you can go ahead and then take a screenshot of this. So I'll give you guys about 5 seconds to screenshot this. 5, 4, 3, 2, 1. And then here's another one, a bit more complicated. 5, 4, 3, 2, 1. All right, I'm not going to be sending out answers to these, but what I recommend doing is, yes, I will allow you to go and flood my email inbox, and you guys could just send me your answers for that, and I'll tell you if you're on the right track or not. Okay, I have gotten a lot of questions from the class or emails. Trust me, I'm not ignoring you guys. I've just been very busy this week. Okay, so now I'm going to go ahead and then transition into the next part of the class, or rather the part before that, which is going to be all the chemistry. Remember, this is organic chemistry, so there is still going to be a pretty healthy amount of chemistry for this exam. So I'm going to start by kicking off with acetylide chemistry. I'm going to start by kicking off. That's very redundant. And not saying I'm calling you guys out, but acetylide chemistry felt like it was something that was quite forgotten because it was covered right before exam 2. And yeah, because he kind of like lectured it before exam 2, I guess that's a lecture where people were kind of checked out on new materials. So you didn't see it, but remember, lots and lots of practice helps you to understand exactly what acetylide chemistry does. Okay, so first, knowing what acetylide chemistry does helps to know what acetylene is. So acetylene is going to be your carbon-carbon triple bond, and or your simplest alkyne, right? And we know that this alkyne has these 2 hydrogens that are going to be pointing out of these. Okay, and we know that we have this bond between an sp hybridized carbon and hydrogen. That's actually going to have a pKa of about roughly 55. 25, not 55. So it's still pretty basic pKa, right? But for relative to other CH bonds, it's actually pretty acidic, right? So in order to functionalize this, we can actually go and then take NaNH2 and NH3 to go and then create an anion. Okay, and then this is what we call our acetylide ion. All right, and we can actually go and then take our acetylide ion and we can react it with some sort of an alkyl halide to go and actually create new carbon-carbon bonds. Okay, now there's a bit of a rule for this, and that's that the acetylide ion can be reacted with primary, very, very important, primary alkyl or allyl halides okay, specifically not vinyl, to make a new carbon-carbon bond. Now, the new carbon-carbon bond, just to check to make sure that you guys are doing this correctly, you could say that it's a new carbon-carbon bond between an sp hybridized carbon and an sp3 hybridized carbon. Cool. So first, I'm going to show you guys the mechanism for how the deprotonation of acetylene works. Not too hard. And then we're going to see how that works in. Okay. So go ahead and feel free to single out a hydrogen here. So your sodium amine will actually go ahead and then deprotonate over here. Okay, the ammonia actually drives the reaction to completion. in order to generate your acetylide ion and some more. Okay. You don't need to include this, but if you're wondering about the sodium just coordinates with that anion there. Okay. Now, when we go and do that, we can actually take this and react it with our primary alkyl halide. Now, for our halides that we can use, we want to use either chlorides, bromides, or iodides. Okay, fluorides actually are not really good, are not really seen here. They're not good at what we call leaving groups because fluorides are very, very basic. Okay, think about acid-base reactions where it's very, very similar to like the concepts that drive these to completion, right? So we call these guys here good leaving groups. Which of these should you use? Really does not matter, okay? If iodide is the best one of the three, but if you want to use chloride, because I don't know, you're feeling like a chloride today, then sure. Also, I've never heard of anyone who feels like a chloride, but be my guest if you do. Okay, so let's go and see how this works. So here, like bromine, okay? Now, what's driving this reaction is the fact that bromine, as you know, has a partial negative, right? This induces a partial positive on this carbon over here. That makes that carbon very electrophilic, okay? If that carbon is electrophilic, it'll want to go in and accept electron density. So now what you see here is that you're going to go in and attack this carbon and then break that bond with carbon-carbon bond. And as promised, you see that this is an sp hybridized carbon, and then this is an sp3 hybridized carbon. So you're making a bond between those two, okay? Very, very important side note. It's a note that we all have to make to ourselves all the time. You know, happens to the best of us, but please count your carbons. It is very, very, very easy in these problems to lose your carbons. So make sure that if you start off with 5 carbons and you're adding in 3, that you have a total of 8 carbons between the steps, okay? If this is a little hard for you guys to understand, think back to our acid-base reactions from earlier in the semester, right? Where we can go in and take our acetylide ion, attack our hydrogen, kick off our bromine, and we end up adding the hydrogen back. And in both cases, you end up kicking off your bromide into solution. Right? It's pretty much the same concept, except now instead of using a proton, we're using a very electrophilic carbon, okay? Driven by the fact that you can form that conjugate base bromide. Cool. So this type of reaction that we see here is called a substitution reaction. You'll be learning a lot more of these substitution reactions immediately following this exam, where you're going to be learning about things like SN1 and SN2. Okay, it's really worth noting some of the things that might happen if you don't use a good alkyl halide, right? So let's say that you go and then use, let's say you use a secondary alkyl halide instead. Cool. So as promised, here is a secondary alkyl halide. And then what actually ends up happening here is that you will not get much of this reaction happening at all. Okay, you still have the dipole. But the reaction that you would like to occur does not really happen. Okay, and that's a couple things. First of all, substitution reactions tend to be very slow under steric hindrance. Second, there is a much more favorable reaction going on here, and that's that we can actually go and then deprotonate okay, in order to go and then end up doing a reaction that we call an elimination reaction. And what drives this to happen is, again, because of the fact that this guy has a pKa of 25. Okay, remember that things that have a pKa above 10 are considered to be pretty basic, right? And if this is basic, we say that this absolutely loves hydrogen or loves protons. Okay, so remember that if there's one thing you guys should know, it's that proton transfers are some of the fastest reactions in organic chemistry. So because of that, if you have too hindered of a halide, then you'll see that this reaction, that the reaction that you want, that substitution, will not occur. Okay, if you have a vinyl halide, okay, you try doing this, there will be no reaction. Okay, and then this is because substitution does not work on sp2 carbon electrophiles. Only do it on sp3. Okay, and then remember that's because that sp3 is the most electropositive of the bunch. All right, so I've shown you guys a bit of the chemistry. If you were to go and write this down in a synthesis, the ideal thing to do would be to maybe, let's say you want to go and then end up with this guy over here. What you would do first is to go and write step 1, NaNH2 and NH3. And then step 2, ethyl bromide. Okay, so something like that, because you see they're trying to add 2 carbons there. If, let's say you start off with your alkyl halide, let's do this. If you start off with your alkyl halide, and then you end up with this, you could just go ahead and then write that by introducing acetylene, and then NaNH2 and NH3. And then these 2 guys will react together first in order to form the ion and then attack over here. Okay, very, very useful synthesis. First one that creates your carbon-carbon bonds. Cool. Now we're going to go and then talk about another carbon-carbon bond-making reaction, and that's going to be Diels-Alder. Before that, any questions about acetylide chemistry? Okay, so let's go ahead and then look at our Diels-Alder. Cool. Now for Diels-Alder, one thing you should know about our favorite organic chemistry professor is that Falzone loves Diels-Alder. Okay. In fact, Diels-Alder and ozonolysis are 2 of Dr. Falzone's favorite reactions for the semester, and you're going to be seeing them pretty much overused from now until whenever you're done taking Falzone's class. So the way that Diels-Alder works is that you're going to have a diene and a dienophile. Okay, the names where this comes from, or like the reason for the naming is that the diene is, guess what, 2 double bonds, so diene, and then dienophile is accepting the electrons from the diene. So this reaction, when run in heat, what's going to happen is that you're going to go and then form some new carbon-carbon bonds. Let's see exactly what we form here. So you go and then either cycle your electrons clockwise or counterclockwise, that does not matter. But what you end up forming is 2 new sigma bonds and then 1 new pi bond. Okay, and then you end up forming overall a cyclohexene ring, right? So that 6-membered ring is a very, very clear giveaway that a Diels-Alder reaction might have occurred. Cool, so some things to watch out for here is your diene. So a question that I get a lot is, oh, what if I draw the diene like this? Is that still okay? The answer is yeah, that's fine. As long as it's not like locked into a ring or something like that. So we end up having these 2 conformations here, which this is called S-trans, and this is called S-cis, okay? And preferably for a diene to react in Diels-Alder, it should be in the S-cis conformation, okay? Similar to things like chair conformations, you have these 2 different conformers that can exist, with the one that exists a little more being your S-trans, right? Because of the fact that you have less steric hindrance. However, if you need to do a Diels-Alder reaction, it will rotate itself into S-cis, no problem. Okay, where you start running into problems is that if you have a ring like this, okay, so here you see that this is S-cis, but that's good because this is actually, because of the ring, it's locked into S-cis. And that's good for Diels-Alder. And then you have this other one over here, which is locked into S-trans. And because it's locked into S-trans, I mean, you can't rotate about the ring. So that one's actually going to be bad for Diels-Alder. Cool. Again, very useful in synthesis. So let's say we have something like this, right? So we see that we have our diene, and then we have a dienophile that contains an electron withdrawing group, like an aldehyde, right? You see that that is actually considered an electron withdrawing group by resonance. So if you were to go in and heat these up, you would actually go and then end up with this cyclohexene ring with an aldehyde that you see over here, right? You're following the same pattern as you did earlier. You see that you form your 2 new sigma bonds here, and then you form your 1 new pi bond here, right? You can also do it with your dienes locked inside a ring. Very classic case, which you guys have seen in Pilot, is the dimerization of cyclopentadiene, right? If you were to go and then run a Diels-Alder reaction on that, connect your diene to your dienophile, okay, you actually end up seeing that these guys will react as usual, and I'll draw it like this first, but then you end up seeing that your product ends up looking like this, okay, where this part of the ring kind of just like bent upwards, and then your other ring looks like this. Okay, so this is a possible type of Diels-Alder reaction where you can use this to make basket compounds or bicyclic compounds, whatever you want to call them. And you see that you are still making those new sigma bonds and that new pi bond. Okay. One thing you guys should know about Diels-Alder also is that Diels-Alder is reversible. Okay, so let's say I wanted to go and then break some ring or break a 6-membered ring with Diels-Alder. You can do that as long as you have, that one pi bond that you need. Okay, so let's say I have, so I'll start off with my simple Diels-Alder, okay. Go and then react that with my dienophile, and then I end up with this 6-membered ring here. If I actually take this 6-membered ring, or that cyclohexene, and I heat it up once again, I will end up reforming 1,3-butadiene and ethylene again as well. Okay, being a testament to Diels-Alder's reversibility. Okay. Cool. So you could do that with any diene and dienophile and cyclohexene, right? Just break it by reversing or form it by doing the forward reaction. Cool. There are some other cases like intramolecular Diels-Alder, or maybe, intramolecular Diels-Alder, or Diels-Alder with alkynes that involve, nuances to the reaction, but it's still generally the same thing. If we have time, I'll have some synthesis examples that we can work on. Okay. Any questions on Diels-Alder before I continue? Yes, as Sam said in the chat, there will be an example of an intramolecular on this week's set. So if I don't get to doing one today, then come to Pilot. I don't have to tell you guys to come to Pilot because you guys are going to come anyway, but definitely come. Okay, now we're going to go and then talk about our another thing with conjugated dienes. That's going to be our thermodynamic and kinetic reactions of conjugated dienes. Okay, so let's say I have 1,3-butadiene here, and I want to react it with HBr. First of all, when you're reacting with things like HBr, it's always really important to go in and specify how much you're using. Okay, do you want to use excess or do you want to only use one equivalent? Okay, so for this, I'm going to be working with one equivalent of HBr. And one of the things I'm not too good at personally is remembering to write one equivalent. So maybe sometimes you'll see that I won't write it and then you'll be like, wait, hold on, write one equivalent or something like that. But make sure that you guys are used to writing one equivalent on your exam when you're working with things like this. Cool, so if I go and then react this with one equivalent of HBr, you know that I'm going to end up forming a carbocation, which looks like this. Okay, so yeah, you guys would know because of the fact that you would simply just take this HBr and react it with one of those double bonds that you have in that starting compound. Cool. So you can get either of this, but one thing that you know that is that it's an allylic carbocation. And you guys know that with allylic carbocations, you can actually resonate them to get another structure that looks something like this. Okay, so hopefully you guys remember to how to draw resonance structures because that's how we can go in and shift that double bond and the carbocation in order to get what we see here. Okay, after you have that, you could take your leftover bromide and then react it in order to get this, either this compound or compound from the one below. This compound. So in terms of some terminology here, so notice that when we went and we added our HBr, in both cases our first proton added here, hence being here in the final product, and then that first proton added here, hence being here in the product. Okay, so when we talk about the relationships between these two, we always say, or we say that the first thing that was added, the proton, is 1, and then the second thing is 2. So we see that this product here is 1, 2. The bottom one, you see that this will be 1, and then we actually have to go in and keep counting each carbon in between. So you get 1 for the carbon with the hydrogen, then 2, 3, 4. This ends up being 1, 4. Cool. So if we say 1, 2, and 1, 4 products, you know what that means. Next question is talking about which is going to be our thermodynamic and which is our kinetic product. And we actually have to look at that based off of both the intermediate and the final product. So for our thermodynamic product, I'll start off with kinetic first. So some characteristics of your kinetic product is that it undergoes the more stable carbocation intermediate. It has the less substituted double bond in the product. Okay. It is overall the less stable product. And it predominates at low temperatures. Okay, so that will be kinetic. Compare that to thermodynamic, where your criteria are going to be similar, except, let's see if I can do this properly. Where your thermodynamic has your less stable carbocation intermediate, your more substituted double bond in your product. And then product stability, remember we're talking about the stability of our products, not our intermediate. It's going to be our more stable product overall. And then this dominates at high temperatures. Okay. So very, very useful to know how to control your regiochemistry. So now looking at these two, when we analyze this, we see that for our kinetic product, we see our more stable carbocation here because it's secondary versus the other one being primary. We see our less substituted double bond in our product here and our more substituted here. Okay, so because of that, we could say that this one is going to be our kinetic product and our red one is going to be our thermodynamic product. Okay, you just go and then you check off all the criteria that we have there. It applies pretty nicely. Now, if I were to just run the reaction at room temperature, I would probably get a mixture of products. And if you're working in chemistry, getting a mixture of products is usually suboptimal because of the fact that you want to have a good, you want to be able to isolate one product, right? One product in higher yields. So to do that, there we go. We can actually go and then encourage a specific temperature for our reaction. Now, for kinetic, we want to work at low temperatures. And as I've said before in Learning Done, usually low temperatures are going to be pretty obviously low, okay? So we're going to see temperatures like maybe negative 78 degrees Celsius, which is pretty damn cold. I can attest for that myself because I've stuck my hand in a negative 78-degree bath before. Or you might see 0 degrees Celsius as well. That's still pretty cold, unless you think that 0 degrees Celsius is warm, then you're weird. And then the bottom one would be something like 80 or 100 degrees. Okay, sometimes you might just see the delta for heat being represented for that with that as well. Cool. So you can see that that's how it works for HBR. One of the points that I've always made also is that the book claims that 1,2 is always kinetic and 1,4 is always thermodynamic. That is absolutely not true. The book is wrong. Okay, so if you look at some examples, like an example of this might be maybe this compound. Where you see that your two products, well, first the intermediate that you end up forming, it's actually going to be the secondary carbocation rather than the tertiary. And the reason you form the secondary is because it can actually resonate. Okay, so here we prefer conjugation over hyperconjugation. Okay, so if you form the tertiary cation, notice that this would not be conjugated. You won't be able to move the double bond. So we have to put our carbocation in a place where we can resonate. I hope that resonates with you. Now, if we go and then draw our other possible intermediate, we see that the other cation ends up being over here. Okay, so yeah, so now we want to go and add in our bromide. And then we end up getting these two products. Again, this one is your 1,2, and then this one is your 1,4. Okay, one of the huge things that you guys see here now is that based off of the criteria that I gave you up here, your less stable carbocation intermediate and your more substituted double bond actually comes from the 1,2. And then likewise, everything else comes from the 1,4. So we see here that 1,2 is thermodynamic and 1,4 is kinetic. Okay, so that's an example of one where, that's an example of a case where it disobeys the fake laws that are given in the book. Okay, all right. Another big thing that you guys can get from this is that even though we're talking lots about carbocations, this can actually work with Br2 as well. And in fact, this is very highly used in synthesis for this class. So if we were to go and then use one equivalent of Br2, so we end up getting that our bromonium ion would form, as you would expect. Okay, and you get one of two cases here. So either, let me copy this real quick. So you're not going to be forming a carbocation. Your bromide can either go and attack at the conjugated site, as you would expect, giving you a product that looks like this, your 1,2 product still kinetic, or your bromide can actually go in and attack at your 4 position, right? Reason why you can attack at your 4 position is because we know this part's partial positive, and you know this will be partial negative, this will be partial positive, and you want to direct your electrons towards the partial positives. So just like in real life, we want to focus on the positives, except here it's just partial. And we want to end up adding our bromides at those positive positions. Okay. So then we end up with our 1,4 addition of our bromides. Okay. Your 1,4 actually ends up being quite useful because you can go and then do some substitutions, as we'll probably see if I have some time to do maybe some examples of synthesis. Well, one last thing before I move on to aromatics, which will be the last big topic for the review session. There is a question that tends to show up on exams that kind of looks like this. Okay, and the question is there thermodynamic or kinetic control for this reaction? Okay, so is there thermodynamic or kinetic control for this reaction? The answer is no. Haha, tricky there probably, or maybe I didn't, which if I didn't, then that's good. But yeah, there is no thermodynamic or kinetic control for this reaction because if you draw the two products, well, I say two products, there aren't actually two products. Your two supposed products would either look or rather, sorry, yeah, there are two products, either like this or like this, right? So two different regioisomers, however, you can't use heat or low heat or low temperatures in order to go and enforce one of them because they both have the same carbocation intermediate and the same number of substituents on that double bond, okay? So no thermodynamic or kinetic control for that reaction. All right, any questions on this before I move on?
Yeah, sorry, could you just walk through like that purple Br2 one again?
Which one?
The bottom one.
Mm-hmm. Yeah, so remember that both of these sides of the bromonium ion are going to be partial positive, okay, because we know bromine is electronegative. It wants electrons back. The only way that you can give electrons back to bromine is by going and actually breaking this bromonium ion. So if this is partial positive, remember opposites attract. So you want to go in and alternate your partial charges. So even though this is a special case, everything else will be alternating. So we have partial positive here, and partial negative, then partial positive. When we attack the partial positive, we end up seeing that we end up moving this bond over here, and then we end up breaking the bromonium ion, which is how we end up getting our bromines adding at those two ends of the compound. Does that make sense?
Yes, thank you.
Cool. Right. I will try and walk through an example of a synthesis problem at the end. I shouldn't spend really too much time on aromaticity, but yeah. So let's go ahead and talk about aromatics. Just writing aromaticity here makes me think about the really delicious steak I'm going to be having after this because I'm very hungry. Okay, so aromaticity. So far what we've seen is that the poster child for aromatic compounds is this little guy right here called benzene. Okay. And with benzene, we have some different ways that we can represent it. Okay, we have these two resonance structures here, right? Either one is correct, but just know the electron cycle. And because of that, we also have this other representation, which is circle benzene. for some really weird reason, there's always this debate on like, oh, like should I draw a line benzene or circle benzene? It does not matter. Just do it, and you can silently judge other people if you want to. But there's many other things in the world to worry about besides whether you draw your benzene to the line or a circle. However, looking at benzene, we can actually deduce 4 different criteria that we can have for aromatic compounds. Our first big criteria is that we have a fully cyclic pi system. Next is that we need to have a ring of all sp2 atoms, which is honestly kind of like a repetition of the first one, but in different words, but helps us out. We must be planar. And we need to have a Huckel number of pi electrons. Okay, or the, I guess, easier way to think of that is an odd number of pi electron pairs. All right, so yeah, with benzene, the way that you could prove that is that you see that our pi system is fully cyclic, right? Kind of hinted at the resonance structures that I drew earlier. You can go and then push everything around fully. Okay. And what's it called? Oh yeah, and then we see that the ring has to be all sp2 atoms. So sp2. You can tell that because each one has a pi bond that is unhybridized and it can be delocalized. All these atoms are sp2. Very good. It's planar. I mean, it's a 6-membered ring, and if you have a 6-membered ring of all sp2 atoms, sp2 is trigonal planar. It won't be what's it called? Yeah, it won't be non-planar unless you have like a much larger ring, which in that case you might have to distort things a little bit. And then your last one is going to be your odd number of pi electron pairs. Well, here you see that you have 3 pi electron pairs, okay, coming from each of these 3 double bonds that you see here. All right, cool. So that confirms that benzene is aromatic. Let's go and then take a look at some other aromatic compounds. Okay. I should also specify that aromatics are very stable. All right, and then we see that for aromatics, we have things like furan. Okay, so again, you have your fully cyclic pi system. You can go in and resonate your electrons all around. I don't have time to draw out all the resonance structures, but you can do it on your own. Also, a ring of all sp2 atoms. That's very important for a very specific reason. It's planar, and then you have 3 pi electron pairs that cycle around the ring. But wait, Juan, what about this guy over here? Does that not delocalize? The answer is absolutely not. Okay, so we see that this lone pair does not delocalize. Because of the fact that, because the oxygen must be sp2 to be in the ring. Meaning if you can delocalize both pairs, it would be sp. Cool. So not ideal for, so like delocalizing that would not be ideal for us, and it would also create a very wacky resonance structure. Cool. So that's why furan is going to be aromatic. Another aromatic will probably be 5, 6, 7. This compound here, right? So 7-membered rings, if they're aromatic, they can actually still be planar because even though 7-membered rings are, kind of large, we want to try and gravitate towards aromaticity as much as we can. So you see that it's aromatic because it is planar, fully cyclic pi system, and a ring of sp2 atoms. So we can go and then draw resonance structures like all over the place, and every atom is sp2. Okay, and you see that our 3 pi electron pairs are just these 3 pi bonds. One last one, a very funky example. This one here, yes, you have 2 positive charges next to each other, but the whole point is that you only have 1 pair of pi electrons, which 1 is an odd number, and it still cycles around the ring. Cool, so that would be a good contender for an aromatic. All right, when we're talking about anti-aromatics, so anti-aromatics are very highly unstable. Okay, and then also the only difference they have between aromatics is that they have an even number of pi electron pairs. Okay, so the most common example of this would be your cyclobutadiene, okay, which you guys might have accidentally used in synthesis. Please do not use this in synthesis; it's very unstable. And we see that we have a fully cyclic system. All the atoms are sp2. It's planar, but we have 2 pairs of pi electrons, which, in case you guys may not remember, for whatever reason, 2 is an even number. So yeah, it's anti-aromatic. Okay. Another example is if we have compound like this, right? So here you see that we have a positive charge, meaning that you don't have any pi electrons there, but it's still part of the pi system. You see that we have these guys over here, and it fits the other criteria. Because you have an even number of pi electron pairs, it's anti-aromatic. And maybe one last example. Okay, here you have this 3-membered ring with a negative charge. Here you have 2 pairs of pi electrons because of the fact that the lone pair here from that negative charge counts. So 1, 2, anti-aromatic. Okay, and then not aromatic. Okay, not aromatic is a huge umbrella. Okay, not aromatic compounds can be stable or unstable depending on what they are. The big difference between that and anti-aromatic, or that and aromatic, is that not aromatic compounds are either not fully cyclic, i.e. not all sp3, or, sorry, not all sp2, or they're not planar. Okay. So let's say we had cyclopentadiene. Okay, for cyclopentadiene, we see that we have, we see that we have a conjugated system that's in a ring. Mind you, if you have a conjugated system that's in a ring, that does not mean it's a cyclic pi system. Okay, so what we see is that we have this that this carbon over here is actually sp3, meaning that you cannot cycle your electrons all around. So because it's not fully cyclic and technically not planar anymore, this is considered to be not aromatic. Okay. Another example. And this is a bit of an interesting example. Is this one right here? Because if we don't assume planarity, if we assume planarity, it's anti-aromatic. Okay, but let's say we don't assume planarity. This molecule is actually not planar. And let me show you why. So trying my best with this drawing. 1, 2, 3, 4, 5. I drew an 8-membered ring instead. Okay, not a great drawing, but good enough. This compound actually is not planar because of the fact that this nitrogen actually kind of like puckers up just a little bit in order to resist anti-aromaticity, right? Okay, so because it wants to resist anti-aromaticity, it actually goes and then distorts itself out of shape so that it's not aromatic and hence not as unstable. Okay, just for reference, in real life, this is sp3. But if we assume planarity, this is sp2. Okay, so those are just two big cases of things that are not aromatic. Okay. Any questions on aromaticity?
So in order for that 7-member one with the nitrogen on it, in order for it to be not aromatic, then planarity cannot be assumed.
Yeah, planarity cannot be assumed. Yeah, this is not actually planar. Okay, I guess we have 4 minutes. I'll quickly show you guys the synthesis problem.
Juan, if you have a second, can you also go over esters and like the TPM for hydrogens on it?
Sorry, what was that? Your audio is kind of.
If you have a second, could you also go over esters and like the TPM for like typical TPM?
Sure, yeah, I'll do that. Yeah, I'll do that now and then I'll do synthesis. Okay, so for knowing how to orient esters and proton NMR, as I told you guys earlier, if you know how to read your shift table, then this should be not that bad for you. Okay, so any protons that show up over here, so these guys, if it's on the oxygen side, then we expect this to show up at around 3.6 to 4.6 ppm. Okay, and if this is on the carbonyl side, then we would expect that peak to show up at around 2.1 to 3.1 ppm. Cool. So you can use that to pretty nicely find the orientations of your esters, right? So if you want to know like which direction the O is in, what I would do is to go and find any peaks between 3.6 and 4.6-ish, right? If you have a peak between 3.6 and 4.6-ish, then you would likely have that at, then you would likely have that on the oxygen side of the ester. You have under corresponding 2 to 3.1, and be a peak that's on the carbonyl side, okay? Again, this is pretty doable with your shift chart, so go ahead and understand your shift chart. All right, because we started a couple minutes late, I will keep you guys for a couple extra minutes, and I will quickly do a synthesis.
Yeah, so if anyone has to go, feel free to like head out. I sent an email earlier with like the link to this Zoom meeting. There's also like a survey you can fill out to get access to the recording. So we'll record these last few minutes of the synthesis problem, but we'll also have synthesis on this week's pilot problem set, so you can get more practice that way. Anyways, if you want to keep going.
Sorry, it's kind of frozen. Let me.
Yeah, it's not updating on my end either. Or, oh wait, there it goes. Okay.
We love the socials Wi-Fi. Okay, give me a second. 1, 2, 3, 4, 5, 6, 7, 8. All right, beautiful. Okay, so here we have a compound, right? And this compound, or like here we have a synthesis, and we see that overall in the synthesis, we're going to be adding some functional groups here. Okay. What I would personally do is to go and then first count your number of carbons. So you start off with 4 carbons, you end up with 8 carbons here. So 4. That means that you're going to have to go in and add in 4 carbons somehow. Okay. You see that you're going to be creating some carbon-carbon bonds, right? Because you have a much longer chain. So what I would personally do is to go ahead and start by kind of like working backwards and see what I can potentially do. So looking at this, let me actually number this: 1, 2, 3, 4, 5, 6, 7, 8. We see that we have this aldehyde on carbon 1, this alcohol on carbon 5, and then this aldehyde on carbon 8. Okay. So what we can actually do is to go and see where everything, or see what could have been here previously. So if we have these terminal aldehydes here, we have some possibilities like ozonolysis. But really, I think the best possibility that you could have here was having added 9 bbn across a terminal triple bond. So if you had a triple bond between 1 and 2 and 7 and 8, and likewise a double bond between 4 and 5, then 9 bbn would give you everything at those positions that you see there. For the alcohol, I will explain why we see the regiochemistry that we do. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. Now, the reason why I put that double bond there is because of the fact that we have a pretty familiar pattern, right? And that pattern is that if I were to go and then add in thermodynamic Br2, well, I just put heat, you could put 80 degrees there as well, that does not matter. I would go and then end up getting my bromides at my 1 and 4 positions here. Okay, so that's just my 1-4 addition of BR2. Now to get from here to here, all I'm doing is I'm replacing these guys with our, acetylenes. So this would be a good time to go and then create our carbon-carbon bonds. So what we can do is to take 2 equivalents of acetylene, right? Because we're making 2 carbon-carbon bonds. And then react it with NaNH2 and NH3 to form your acetylide ion. Yes, you do need to show the synthesis of the acetylide ion. So make sure you guys go ahead and do that. Okay. In doing so, you see that your acetylide would just go and then replace at each of these positions. And doing so would end up getting you this compound that you see here. Cool. So pretty simple synthesis, but at the same time, might be a little confusing if you're not used to common patterns. So make sure that you guys are able to kind of maybe, work on this by like maybe working forward and backwards at the same time to kind of go in and make your synthesis problem a little smaller. And, doing things like numbering carbons or recognizing patterns really helps you out a lot. What you cannot do is compartmentalize, meaning that you need to know all of your reactions from, early on in the class, and you need to be able to go and then govern and understand like why regiochemistry works the way it does, or things like that. Cool. So nice little primer on how to solve, typical synthesis problem, but you will be doing more synthesis, more fun synthesis in Pilot this week. All right, any questions about the synthesis? All right, well, this is a fun review session. Hopefully it ended off a rather fun weekend for everyone. If you guys have any questions about today, feel free to email me or your Pilot leader. You can also, you're also welcome to go and send your answers to those NMR problems that I showed earlier. Cool. Make sure you guys actually work them out. Don't just email me asking for what the answer is, because I will not answer that. Okay. All right. Have an awesome week. Hope to see a lot of you at Learning Den for some more practice before your exam. And yeah, enjoy the rest of your Sunday.